Hello and welcome to AI-300, Operationalize Machine Learning and Generative AI Solutions. We're so glad you've joined us. I'm Barbara Andrews, a Microsoft technical trainer here at Microsoft, specializing in data and AI, and I'm excited to guide you on this journey from experimentation to real-world impact. In this course, you'll move beyond building models to truly operationalizing AI, learning how to deploy, monitor, scale, and govern machine learning and generative AI solutions with confidence using Azure. Through hands-on demos and practical scenarios, you'll see how production-ready AI powers real business outcomes, whether you're detecting fraud, personalizing customer experiences, or safely deploying generative AI at scale. Let's get started and turn your AI ideas into reliable, secure, and value-driven solutions. Before we dive in, let's set the stage for what you'll walk away with from AI-300. In this course, you're going to move from building models to running AI in the real world, training and optimizing machine learning solutions in Azure Machine Learning, automating end-to-end MLOps with pipelines and GitHub Actions, confidently deploying and monitoring models in production, and stepping into the next wave of AI by building, evaluating, and fine-tuning generative AI agents using the Microsoft Foundry. Every objective is designed to help you deliver AI that's not just impressive in a notebook, but reliable, scalable, and valuable in production, exactly what modern organizations expect from AI practitioners today. This course is designed for data and AI practitioners who are ready to take models from development to production and want to do it in the right way. If you work with Azure Machine Learning to train, deploy, and monitor models, track experimentations, and manage lifecycle with ML Flow, automate infrastructure and ML Ops using Bicep GitHub Actions in Azure CLI and the Python SDK, or are beginning to build and evaluate AI agents with Microsoft Foundry, you're exactly the audience for AI-300. This course assumes you're hands-on, curious about automation and scale, and focused on delivering ML solutions that are reliable, repeatable, and production-ready, not just successful in a notebook. We'll start by designing a machine learning training solution, learning how to think architecturally about data, compute, and reproducibility before any code is written. From there, you'll experiment with hands-on in our Azure Machine Learning, iterating quickly as you explore different modeling approaches. You'll then shift into optimizing model training, focus on performance, cost, and scalability before going deeper into hyperparameter tuning. We're using sweep jobs to systematically find the best possible model. Along the way, the labs will reinforce every concept as you identify the best classification model, optimize its training, and fine-tune it using automated hyperparameter search, mirroring exactly how real-world ML teams move from idea to high-performing production-ready models. Next, we'll shift from individual experimentation to operational automated machine learning at scale. You'll learn how to build and run pipelines in Azure Machine Learning to create repeatable end-to-end workflows that step back to plan and prepare a complete MLOps solution that aligns people, processes, and platforms. From there, you'll automate model training using GitHub Actions, turning manual steps into reliable CI/CD workflows, and finally deploy and monitor models in production, ensuring performance, reliability, and visibility over time. The labs will bring this to life as you run pipelines hands-on and deploy a model to a live endpoint, mirroring how modern ML teams move from experimentation to fully automated, production-ready AI systems. Next, we'll bring everything together as you step into Gen AI Ops, the discipline of running generative AI and agents responsibly at scale. We'll start by planning and preparing the Gen AI Ops solution, focusing on governance, safety, and lifecycle management from day one. From there, you'll learn how to manage prompts and agent configurations in the Microsoft Azure Foundry using GitHub, treating prompts and agents as versioned, testable assets, not one-off experiments. Finally, you'll get to evaluate and optimize AI agents through structured experiments, measuring quality, consistency, and behavior so your agents improve reliably over time. The labs will walk you through real-world Gen AI workflows, designing Gen AI Ops foundations, and developing prompt and agent versions, and optimizing prompts for repeatable production-ready performance. The exact skills teams need to know to move forward in generative AI, from hype to a trusted business capability. Lastly, we will see where your generative AI solutions become measurable, observable, and continuously improvable. You'll learn how to automate AI evaluations using Microsoft Foundry and GitHub Actions, bringing rigor and repeatability to how agent quality is tested over time, not just manually reviewed. From there, you'll monitor and trace your generative AI agent, gain visibility into behavior, performance, and decision paths so issues can be detected and addressed early. Finally, you'll optimize AI agents through fine-tuning, closing the loop between evaluation and improvement. The labs make this tangible as you automate evaluations with cloud-based evaluators, trace real agent interactions, and fine-tune models for better accuracy and consistency, equipping you with the exact skills needed to operate generative AI confidently and responsibly in production. To access all the course materials in one place on Microsoft Learn, please see the link on this slide. It's on the left-hand side. We have our course, AI-300 at the very top there. You can do a search on that. The course also includes hands-on labs with detailed instructions, plus open lab repositories for both MLOps and Gen AI Ops that you can revisit anytime to reinforce your skills. There are many more labs available in the links on the right that you can see here on the screen for this course. So you have a ton of hands-on exercises to choose from for optimal ML learning. This course is also designed to help you succeed in the AI-300 Microsoft Certification exam. The exam focuses on the real-world skills you'll be building throughout this course, designing and implementing MLOps and Gen AI Ops infrastructure, managing the machine learning model lifecycle, ensuring quality and observability, and evaluation for generative AI, and optimizing models and agents for production performance. As you prepare, I recommend using the available exam prep videos, the official study guide noted here at the bottom of the slide, the exam sandbox, and the practice assessment to build confidence with your exam experience. Everything we'll cover aligns directly to these study areas. Are you ready to begin the AI-300 operationalizing machine learning and generative AI solutions? Let's start this incredible journey. Welcome to our first learning path in operationalized machine learning and generative AI solutions. In this session, we will bridge between experimentation and real-world impact, showing you how to turn powerful machine learning and generative AI ideas into production-ready solutions. You'll explore how to operationalize models so that they're secure, scalable, monitored, and continuously improving, moving beyond notebooks into systems that deliver real business value. In AI-300, this is where your role shifts from AI builder to AI engineer, focusing on deploying, managing, and governing AI solutions that organizations can trust and rely on every day. So let's get started with this session. This agenda sets the foundation for how modern enterprise-grade machine learning actually gets built in Azure. In this part of AI-300, we're going to walk through the full training lifecycle, from designing a robust training solution to running and tracking experiments, optimizing performance, and fine-tuning models with hyperparameters that truly matter. The focus here is not theory, but practice, learning how to iterate confidently, measure this at work, and systematically improving our models using Azure Machine Learning so they're ready to scale from experimentation into real-world production scenarios. This is where very successful ML solutions begin, by designing the training approach the right way. Let's get started. Here we see the full machine learning lifecycle, highlighting that successful ML is not a one-time activity, but an iterative, continuous process. It starts by clearly defining the problem, then moves through getting and preparing data, training the model, integrating it into an application, and finally monitoring performance in the real world. While this diagram looks linear, in practice, you're constantly looping around and back to the beginning. Monitoring results may reveal data drift, performance issues, or new patterns that require retraining, or even redefining the problem. Azure Machine Learning supports this end-to-end flow, especially during experimentation and development, where data scientists need hands-on access to raw data, flexible feature engineering, and rapid experimentation. As a practical example, imagine building a customer churn prediction model. During development, you might use Azure Machine Learning to explore raw customer data, experiment with the features, and train multiple models quickly. Once the solution moves toward production, data preparation typically shifts to more scalable services like Azure Synapse Analytic Pipelines or Azure Databricks Jobs, which prepare data on a schedule using distributed compute. That curated data is stored in our Azure Data Lake and then consumed by Azure Machine Learning for training and retraining. This separation of experimentation versus production scale is critical in real-world solutions, and understanding where each Azure service fits is a key skill you'll build in this course. Defining the problem is the most critical step in the entire machine learning journey, because a well-defined problem sets everything up for success. In this stage, you will clarify what the model should output, what type of machine learning task fits that outcome, and how you'll measure success. Is the goal to predict a category, a number, a future value over time, insights from texts, or patterns in images? By aligning your data with the expected outcome, you can confidently choose between common tasks like classification, regression, time series forecasting, computer vision, or natural language processing. Getting this step wrong, and even the most sophisticated model won't deliver meaningful results. For example, consider a retail business trying to reduce customer churn. If the outcome is, will this customer leave? Yes or no? The problem is classification. If the business wants to predict how much revenue a customer will generate, that's regression. Forecasting weekly sales trends becomes time series forecasting. Analyzing in-store camera images falls under computer vision. And extracting sentiment from customer reviews is an NLP task. This slide emphasizes that before touching data or training models in Azure Machine Learning, success starts with clearly defining the problem you're solving, because the right question leads to the right model, metrics, and business impact. Getting and preparing the data is where raw information turns into something a machine learning model can actually learn from. And it's often the most time-consuming but most impactful step. Here we see three critical decisions: where the data lives, what format it's currently in, structured, semi-structured, or unstructured, and what final shape the data must take to train the model effectively. Real-world data rarely arrives ready for training. It often needs to be extracted, cleaned, reshaped, and enriched so that the model sees consistent, meaningful patterns rather than noise. Making these decisions early ensures your training pipeline is repeatable and aligned with the problem you've defined. A practical example is building a time series forecasting model for predictive maintenance using our IoT sensor data. You might start by extracting temperature readings from machines using JSON objects emitted by IoT devices. Those JSON files are then converted into a tabular format and then transformed to calculate the average temperature per machine per minute, creating a clean, model-ready dataset. That final dataset becomes the input for training in Azure Machine Learning. This step shows why data preparation isn't just technical plumbing. It directly determines whether your model can detect trends, anticipate failures, and deliver real operational value. Choosing how you serve data to machine learning workflows is a foundational design decision that directly affects scalability, cost, and performance. Here we see one of the cloud's biggest advantages: separating compute from storage. By decoupling the two, you can scale compute up from intensive training jobs and shut it down when it's not in use, without duplicating data or paying for idle resources. When training models and services like Azure Machine Learning, Azure Databricks, or Azure Synapse Analytics, data is typically stored in Azure Blob Storage, Azure Data Lake Storage Gen 2, or Azure SQL Server. These options are the most commonly used for new machine learning projects because they integrate cleanly with analytics and ML tooling while supporting secure, scalable access. For a practical scenario, imagine training a predictive maintenance model using historical sensor data. The curated training data must live in Azure Data Lake Storage Gen 2, serving as a centralized, low-cost repository accessed by Azure Databricks for large-scale feature engineering, and Azure Machine Learning for model training. Compute clusters spin up only when jobs run, then shut down automatically once complete. While many Azure services can store and serve data, these three storage options cover most ML scenarios and provide a strong starting point. Knowing when to choose each and how to plug them into ML flows is an essential skill that we must have here in AI-300 as you design solutions that scale from experimentation to production. Designing a data ingestion solution is about building the pipeline that keeps your machine learning models fed with fresh, reliable data automatically and at scale. Here we see a common and proven pattern: extract raw data from a source like a CRM system or an IoT system, transform and prepare it using services such as Azure Synapse Analytics or Azure Databricks, store the curated data in an Azure Blob Storage, and then use Azure Machine Learning for training. Think about ingesting early and separating extraction, transformation, storage, and training ensures your solution is flexible, repeatable, and ready to grow as data volumes increase. For example, imagine a manufacturing company predicting equipment failures. Sensor data is continuously extracted from machines, transformed nightly into Azure Synapse Analytics to clean and aggregate readings, and stored in blob storage as training data ready sets. Azure Machine Learning then trains and retrains models as new data arrives. So here's a pro tip. This architectural thinking should happen before training begins. Designing how data is automatically ingested and prepared makes the transition from experimentation to production far smoother. By planning for automation up front, you avoid fragile manual workflows and ensure that your model is production ready the moment it delivers value. Training a machine learning model is a disciplined end-to-end process, and here we see the full story clearly. It starts with loading and inspecting the data, ensuring you understand what you're working with before making the decision. Next comes pre-processing, while raw data is normalized and cleaned so the model can learn consistently and fairly. The data is then split into training and test sets, a critical step that protects accuracy. With the foundation set, you choose an appropriate algorithm, such as two-class logistic regression, and train the model to uncover patterns in the training data. Once trained, the model is scored against the test data to generate predictions, and finally evaluated using performance metrics to determine whether it's accurate, reliable, and ready for real-world use. A practical example is predicting whether a patient is at risk for diabetes. You might start with the diabetes date set, normalize the numeric features, and then split the data into training and test sets. A two-class logistic regression model is then trained to learn patterns associated with positive or negative outcomes. Once trained, the model scores new patient records and is evaluated using metrics like accuracy or recall to understand how well it performs. This structured workflow highlights that training isn't just about picking an algorithm, it's about building trust in your model through repeatable, measurable, and well-governed steps. Choosing the right service to train a machine learning model is less about which tool is best and more about which tool fits your scenario. Here we highlight clear decision points to guide that choice. If a pre-built, customized model already meets your needs, such as vision, speech, or language, Azure AI services can dramatically reduce the development time. If your goal is to keep data engineering and data science unified in one platform, or you need distributed compute for very large data sets, Microsoft Fabric or Azure Databricks are strong fits, especially when working with PySpark. When you need full control over model training, experimentation, versioning, and deployment, Azure Machine Learning shines, particularly if Python is your preferred language and you value an intuitive UI to manage the entire ML lifecycle. For example, imagine building a fraud detection solution. You might start with Azure Databricks to process massive transaction data sets using distributed compute, and then transition to Azure Machine Learning to fine-tune, track, and deploy a custom model with full governance. If teams want to move models seamlessly between platforms, MLflow bridges Databricks and Azure Machine Learning with ease. While many factors influence service choice, organizational standards, skills, scale, and timeliness, these guidelines help you to confidently match the right Azure service to the right problem, ensuring efficiency from experimentation through production. Choosing the right compute is a make or break decision in any machine learning project, and now we see exactly how to think about it strategically. The first decision is CPU versus GPU. CPUs are cost-effective and perfectly sufficient for smaller, structured, tabular data sets, while GPUs shine when working with unstructured data like images or text, and dramatically accelerating training times. From there, you decide between general purpose or memory optimized machines. General purpose compute offers a balanced CPU to memory ratio, making it ideal for experimentation, testing, and smaller data sets. Memory optimized options provide a higher memory to CPU ratio, which is essential for large in-memory analytics and data-heavy workloads. For distributed processing at scale, Spark Compute powered by services like Azure Synapse Analytics or Azure Databricks, comes into play with its driver and work node architecture, enabling parallel processing across massive data sets. Remember to continuously monitor and adjust compute utilization because the model training is iterative and resource needs evolve as experiments grow more complex. A practical use case could be a data scientist team building customer churn prediction models. Early in development, they start with a CPU-based general purpose compute and explore features and test algorithms on smaller samples of customer data. As the dataset grows and in-memory feature engineering becomes more intensive, they switch to a memory-optimized compute. When scaling to millions of customer records, they move to Spark on Azure Databricks to process data efficiently across distributed nodes. Throughout the process, they monitor utilization and adjust compute sizes to balance performance and cost, ensuring the model trains faster without overspending. Thoughtful compute decisions directly impact speed, scalability, and success in real-world machine learning projects. Integrating the model is the moment where machine learning delivers real value by becoming part of an application that users and systems can actually interact with. Here we see a trained model is deployed to an endpoint in Azure Machine Learning, exposing it as a service that applications can call. An app sends a request to the endpoint. The hosted model generates a prediction, and the response is returned almost instantly. This interaction can support real-time endpoints for immediate predictions or batch endpoints for large-scale asynchronous scoring. Either way, integration is simple and consistent. Any application can consume the model using a standard API call. For example, imagine a mobile banking app that detects potential fraud. As a user submits a transaction, the app calls a real-time Azure Machine Learning endpoint with transaction details. The model evaluates the data and immediately returns a fraud risk score, allowing the app to approve, flag, or block the transaction in seconds. Here we have highlighted a critical shift in the ML lifecycle. Models are no longer experiments in notebooks, but reliable services powering decision-making across web apps, mobile apps, and enterprise systems through secure, scalable endpoints. Deploying a machine learning model is where strategy meets reality. And here we see it in one of the most important architectural decisions you'll make: real-time versus batch deployment. Real-time deployments are designed to generate predictions instantly as new data arrives, making them ideal for interactive applications like websites or mobile apps where users expect immediate responses. Batch deployments, on the other hand, process data in groups, scoring large volumes at once and storing the results in files or databases for later use. The right choice depends on a critical question: how often should predictions be generated? How quickly are results needed? Should predictions happen at one time or in bulk? And how much compute power does the model require? These questions help you align latency, scale, and cost with real business needs rather than defaulting to a one-size-fits-all approach. As an example, to detect fraud in credit card purchases, predictions must be generated in real time. Each transaction is scored individually, results are needed immediately, and sufficient compute must be available to handle spikes in traffic without slowing approvals. In contrast, the same organization might run a batch deployment overnight to analyze daily transaction histories, identify fraud patterns, and flag accounts for review. That batch job generates predictions in bulk, tolerates long processing times, and can use lower-cost compute scheduled during off-peak hours. By choosing the right deployment model for each scenario, teams balance speed, scalability, and cost. Monitoring a model is what keeps machine learning reliable, relevant, and trustworthy once it's in production. Models don't fail overnight. They slowly degrade as real-world data changes, which is why tracking performance metrics like accuracy, precision, recall, or the F1 score is essential. A gradual drop in these metrics is often the earliest sign that something is shifting. Monitoring also helps detect data drift, where input features change over time. For example, seasonal shopping behavior or market fluctuations and label drift, where outcome distributions start to look different than what the model was trained on. Even more subtle but critically important is the concept of drift, where the relationship between inputs and predictions change, such as evolving customer behavior or new business processes. Consider a loan approval model used by a financial institution, and over time, economic conditions change and customer profiles shift, causing accuracy to slowly decline. By monitoring metrics and setting retraining triggers, such as retraining when accuracy drops below 80%, the team can respond before business impact occurs. Incorporating newly labeled loan outcomes during retraining helps the model stay current, while scheduled retraining, for example, quarterly, protects against unseen changes, even when metrics appear stable. Here's the key MOps principle. Monitoring is not a one-time task. It's an ongoing process that ensures models continue to perform as expected in dynamic real-world environments. In this case study summary, Designing a Diabetes Detection Model at Prosware, we're building a mobile application designed to help doctors diagnose diseases faster and more confidently. The vision is simple but powerful. A doctor enters a patient's medical measurement into a mobile app. The app uses machine learning to determine whether the patient should be screened for diabetes. You've been hired as the lead data scientist to design the model training solution behind this experience. The app interface already hints at the data available, clinical and demographic factors such as pregnancies, plasma glucose levels, blood pressure, BMI, insulin levels, age, and diabetes pedigree function. After clicking Analyze, the app returns a prediction, for example, yes with 89% certainty, highlighting both the diagnosis outcome and the confidence level. Now comes the critical challenge. How do we train a reliable, responsible, and clinically useful ML model that can accurately detect diabetes? This is not just a technical problem. It's a real-world healthcare scenario where accuracy, interpretability, and trust matter. To train a model that detects diabetes for Prosware's mobile app, treat the task as a supervised binary classification problem using historical patient records labeled with a confirmed diabetes outcome, yes or no, and train only on the same clinical inputs the app will collect to avoid data leakage and ensure the model works in real life. Supervised binary classification was selected because the model is trained on labeled historical patient data and must predict one of two discrete outcomes, diabetes or no diabetes, often expressed with the probability to support clinical screening decisions. Prosware is now ready to move from we have patient data to we can train a diabetes detection model. And the first make or break step is ingesting the right data in the right shape, securely, and at scale. Based on the slide requirements, number one, current data is in a patient database. Number two, data scientists use Python and CSV files. And number three, the design must be future-proof, scalable, and extract privacy-sensitive data into Azure storage. What would be the best ingestion approach? Consider an automated ETL or ELT pipeline using Azure Data Factory or Azure Synapse pipelines that performs scheduled extracts from the patient database and lands curated CSV files in Azure Data Lake Storage Gen 2. The logic is straightforward. If the source is a database, we need a managed service built for reliable extraction, incremental loads, scheduling, retries, monitoring. And if the consumers want CSV, the pipeline should standardize output format. And if privacy and scale matter, the landing zone must be Azure Storage Platform designed for secure, governed analytics at enterprise scale. Critical questions that this choice answers. How will we repeatedly extract new updated patient rows without manual effort? Incremental scheduled pipelines? How will we ensure the training team gets analysis-ready CSVs consistently? Maybe schema-controlled export and validation? And how do we protect sensitive data while still enabling ML work? Maybe what we're going to do is extract only the required fields, apply de-identification where needed, secure storage access, and also make certain we can audit it. Choosing Azure Data Factory or Synapse pipelines with Azure Data Lake Storage Gen 2 and curated CSV outputs directly satisfies every stated requirement by providing a scalable, repeatable, and secure ingestion path from the patient database. When designing a data ingestion solution, it's important to focus less on selecting a specific service and more on understanding the requirements and constraints that drive architectural decisions. Factors such as data volume, data format, security, scalability, transformation needs, and downstream consumption all influence the final design. So let's take a look at both of these questions to further discuss why we have selected the data ingestion solutions that we did. So the first question, which storage solution would you recommend to store the data? Azure Data Lake Storage Gen 2 is recommended because it can store large volumes of CSV data at a low cost while supporting a hierarchical namespace, which enables folder-ready organization, granular access control, and better security governance. This makes it well-suited for analytics and machine learning scenarios where multiple teams and tools need controlled access to shared data. Question 2. Which tool would you recommend we use to move the data? Azure Synapse Analytics is recommended because it can connect to source systems through APIs, orchestrate data movement, and apply transformations as part of the ingestion process. This allows data to be efficiently landed in the Azure Data Lake in an analytics-ready format, making it easy to consume by Azure Machine Learning or other downstream analytic tools. In this case study, the goal is to design a data ingestion approach that sets a team of Python-first data scientists up for success while still meeting expectations for clarity, auditability, and repeatability. The key requirements on this slide point to a solution that keeps the landing zone simple and broadly compatible for downstream model training. It should also offer a UI for operational use and transparency, and it supports notebooks, scripts, so that the team can keep full control of how the data is prepared and how models are trained. When considering the requirements for the team, Azure Machine Learning is recommended because it's designed for Python-first data scientists and does not require SQL or Spark expertise. It allows the team to train classification models using familiar Python libraries and workflows, minimizing ramp-up time and reducing technical friction. For preferred tooling, Azure ML supports Jupyter notebooks and scripts, giving data scientists full transparent control over how models are trained. Built-in experiment tracking, logging, and reproducibility make it easy to explain and audit exactly how a model was built, which is critical for governance and review. And for compute, Azure Machine Learning provides managed notebook environments and scalable compute, allowing the team to start quickly in Jupyter and seamlessly scale training workloads as needed without changing tools or workflows, while maintaining consistency and oversight throughout the model lifecycle. Overall, Azure Machine Learning is recommended because it uses Python-focused data scientists train, track, and audit models using Jupyter models and scripts while providing scalable, governed compute without requiring SQL or Spark expertise. The goal here in Choose the Model Training Service is to enable data scientists to efficiently train and explain a diabetes prediction model while maintaining flexibility to scale and operationalize the solution over time. To answer the questions on the slide, we need to first answer these two questions. Number one, who is the team and how do they prefer to work? And then number two, what are the model's compute and scalability needs now and over time? Answering these questions will help us to find the answers to the questions on the slide. So, first question, what tool should we use to train the model that predicts diabetes? The recommended answer is Azure Machine Learning because it allows data scientists to train the model using Python in native AML Jupyter notebooks, which aligns with their existing skills and preferred way of working. Azure ML provides full control and transparency over the training process while automatically tracking experiments, making the model easy to explain, reproduce, and audit. Question number two, which compute would you recommend to train the model? The recommended answer is a CPU-based compute instance for initial model training because the workload can be run interactively in a notebook and doesn't require GPUs. As the solution matures, compute clusters can be used to train the model with scripts in the production environments, allowing the team to scale training jobs without changing tools or workflows. Let's consider how we could design a model deployment solution. A doctor enters a single patient's information, such as age and BMI, and clicks Analyze to get an immediate diabetes prediction during a consultation that typically lasts under 10 minutes. Those requirements point to an interactive user experience where the speed and reliability matter more than processing large volumes of records at once. Each consideration here affects the deployment solution. Because predictions are triggered on demand, the model should be deployed for real-time online inference behind an API rather than batch scoring. Because doctors need answers quickly, and usage is unpredictable, the endpoint should always be available for low latency, pre-provisioned compute and the ability to scale it out if many doctors use it concurrently. Because each request is for one patient at a time, the solution should be optimized for small, single record requests. It is recommended to deploy the diabetes prediction model as a real-time online endpoint using Azure Machine Learning managed online endpoints. This solution meets all the requirements because the application requires on-demand, low-latency predictions triggered by a doctor during a live consultation with the model always available regardless of when it's accessed. A managed online endpoint exposes the model through a REST API optimized for single request, synchronous inference, runs an always-on CPU, no GPU required, and can be scaled out automatically if multiple doctors use the app at the same time, making it the best fit for this interactive patient-by-patient prediction scenario. Here are two questions that should be answered when designing a model deployment solution. Remember that our scenario focuses on a doctor-facing mobile application where a diabetes prediction is requested during a live consultation. The deployment decision must support speed, reliability, and simplicity to ensure a smooth clinical workflow. Here are the 2 questions to consider. What type of predictions are needed by the mobile application? And the answer could be the application needs real-time, on-demand predictions because each prediction is triggered by the doctor's action and must return immediately while the patient is present. Batch or offline predictions would not meet this interactive requirement. And then our second question, what kind of compute should be used for the deployed model? And the answer could be the model should run on always available CPU compute, which provides low latency for single request inference and is cost-effective for this type of workload. GPUs are unnecessary as predictions are made one patient at a time and do not involve heavy parallel processing. Model deployment solution here could be to deploy the model as a real-time Azure Machine Learning managed online endpoint running on an always-on CPU compute, enabling fast, on-demand diabetes predictions for a single patient during live doctor consultations. Now it's time for our knowledge check. Question 1. Every minute, a JSON object is extracted from an Internet of Things device. What is the type of data that is extracted? Answer: semi-structured. Question 2. Which tool allows quick iteration over featurization in algorithms by providing data and adjusting configurations? Answer: automated machine learning. This section brought together a full picture of how machine learning solutions are designed for real-world success, from ingesting and serving data to choosing the right development environment and compute, and finally integrating trained models into applications. You learned how thoughtful architecture choices early on enable scalability and efficiency, how different Azure services support experimentation and production needs, and how deployment via endpoints turns models into consumable services. Together, these concepts emphasize that building effective ML solutions isn't just about training models. It's about designing end-to-end workflows that are scalable, maintainable, and ready to deliver business value. Thank you for joining us in this session. To continue your learning, watch other videos in this course or explore more on Microsoft Learn at aka.ms/learn.